So this course is actually continuation of what I taught last semester, but it will be at a higher level because it's more at a level where there is a discussion of advanced topics and whatever is going on in this particular field in recent years. What I discussed in the previous course was things that were some 30-40 years old, but they were the foundation of what the subject has come to be. And to understand what I will be teaching in this course, you have to know that material. Okay, whether you took that course or you studied all that stuff on your own doesn't matter, but you have to be familiar with that material. That is one part. Yeah, let me write down the topics that I intend to cover. So I put it in the email broadcast anyway, but there are three areas which I want to cover. One is new topics of quantum algorithms. The topics which I discussed in the previous course, basically Shor's algorithm and Grover's algorithm, they were major breakthrough in terms of bringing in new concepts, but after that nothing as big as those algorithms has happened, even though probably 30 years have gone by. But people have devised various strategies to deal with specific problems, and they are becoming important in terms of connecting them to applications. So, for example, in this case, there are what are known as randomized algorithms, which use random numbers and random walks, etc., to cover various possibilities. Then there are variational methods which may not solve the problem exactly, but which can provide useful bounds on various types of results. Then there are relations to machine learning methods, which are becoming popular these days, and they focus on certain type of problems. There are a lot of applications to problems which can be defined using matrices, linear algebra essentially, and solving them in an efficient manner. So there are various topics which I will go through. The second part is quantum error mitigation. Okay, this is different than quantum error correction. Quantum error correction is actually much more systematic method where you can rigorously prove certain results, and given that the procedure can be implemented, you can have a scenario where the error rate can be pushed all the way to 0, and that leads to the so-called fault-tolerant quantum computing, and that is a long-term goal of the whole technology anyway. But there is a separate course on quantum error correction, so I'm not going into that discussion in this course. those who are interested can take that other course. Here the aim is just mitigation. It is a much more modest target, that you identify dominant sources of error and keep them under control. The error won't go to zero in any particular sense, but as long as you can keep them within certain bounds, you can still extract some useful results. And this is the strategy which is being used these days in many of these quantum devices that are being made. They are not perfect, we know that, but we want to still use them. How you can get the best out of those devices. It's some part heuristics, some part is a development of many kind of tricks, but the job is to keep the errors under control. Sometimes it may be just a simple task like there is too much environmental disturbance, well, you shield your instrument as well as you can. And those are the first steps in this direction. It's basically a reduction of the error, provided you know something about the type of noise which is present. And third topic will be a discussion of various hardware platforms for quantum devices. Here you need to know certain dynamical description of the components that you are going to use, and what are the relevant properties which will exhibit the quantum degrees of freedom, and how you are going to put them together. So it is subjective choice in that particular sense. But then what I'm going to discuss is the theoretical background for those kind of choices. Real hardware will be a job for demonstrating something in the lab, which I'm not going to go into. But theoretically, you can understand various principles and fundamentals which are being used, and many things have been explored over the years. I will go through them sort of one by one. I think it all started with NMR computing. It had a limit, but many things were demonstrated using NMR technology. Then the superconducting qubit devices are popular these days. They have their own requirements. Then there are photonic systems where you use lasers and optics and all related machinery connected with that. Then there are ion trap and neutral atom settings, which are more in the analog domain rather than in the digital domain, but you can do many interesting things with them as well. And then there are different scenarios or other framework like adiabatic computing and measurement-based computing, which look very different from the circuit model, which is analyzed most of the time. But they can also be directly implemented in hardware, and they have their own interesting features. So I will cover this kind of topics in some manner, up to some detail, and that will be the last component of the course. So that is roughly the content of the course. That's all I can point out. And of course, if you have any specific topic or any other thing which you might have read somewhere or looked up somewhere, you can ask me and I will try to explain those things in some sense as the course goes along. But the sequence of the lectures will be something in this particular order that I will follow. Okay, so yeah, that's about it. Do you have any questions on anything which I said so far? Okay. So let me then begin with rather simple topics, and the first part in these algorithms are a subject which is called randomized algorithms. This is a extension of the conventional description of computational theory, and in the sense that it has access to some random number generator. The conventional formulation which I discussed in the previous course was all deterministic. Start with some input, apply some logic gates, and you will have some output. The output can be probabilistic, but still the sequence of operation was more or less deterministic. So here you are adding a new resource, which is basically a random number access that at any stage in the algorithm you can basically toss a coin and decide what to do depending on the result of the coin toss. Okay. So it's a new kind of a resource, and of course if you add a new resource, well, you can hope that I will be able to do more things. So these are problems which has branches. The common programming steps they have that if something, do this, otherwise do something else. But that if something is in the determinist algorithm, some function of the input variables or whatever you have, here you will just toss a coin and say, okay, if the coin comes up heads, I will do this. If it comes up tails, I will do something else. And
yeah. Here, at the time, only one branch executed. At the time, only one branch is executed.
Yeah. Classically, the quantum version will do something else, and you have to figure out what happens in the quantum version. In the classical algorithm, you can execute only one branch at a time. So the question is how much more you can do. Okay? And that's a problem which even classically is not settled. but you can make a trivial statement that if I'm going to add some more capability, it can't do any worse. Okay, whatever is possible is already there, so something more will be possible, and that statement is summarized by this complexity label, that the so-called polynomial resource problems are a subset of this new class which includes random numbers. It has been called bounded probabilistic polynomial. So because it's going to do some random number sequence, you are not going to always have deterministic answer. It will give some probabilistic results. So there will be bounded area, there will probability of success, and then after that it is still polynomial, and the more explicit label for this class BPP is that the success probability is greater than some number which is bigger than half. Typically people write 2/3. Why bigger than half? Because if the success probability was half, I can skip all the calculation and just coin toss will be giving me the result. I don't have to do any work at all. So you need little bit more to say that this algorithm is useful. And having a finite number over here can then give a scenario that I can run the algorithm a multiple number of times and make the success rate as close to 1 as possible. Okay, so this is again a trivial calculation, but I can say that if there are k trials and so I run this algorithm with success probability greater than 2/3 some number of times. I wrote that number as k, and every time it will give me some result, and I will select the result by majority rule. So then what is the success rate of this scenario? And that is very easy to work out. The majority rule is a very simple technique to take powers whenever probability distributions are concerned. So when will the majority rule fail? Well, I executed k trials, and a majority of them have to fail for the final result to be wrong. And that will happen. Well, how often that will fail? Well, you can say it's k by 2. You have to take an integer, but that is fine. And the probability of failure was less than 1/3 by this particular definition. So I can say that how many times this majority rule will fail. So this will be like 1/3, and at least k over 2 have to fail. So the success rate will be 1 minus 1/3 to power, and this can be made small, as close to 0 as possible, And since k is in the exponent, the total rate will be, the effort will go up by a factor of k, but it will be log of the final error, essentially what it is. So, log of, well, I have to write 1 by epsilon. I can calculate what is the failure rate. It is this object, 1 minus that is the success rate. How does it depend on the number of trials? Well, this is in the exponent, so I can bring it down by saying that if this one is epsilon, k will be like log of 1 over epsilon. Log to some basis. Here it is 1/3, but it doesn't matter, some number. They are all related. But the main point is the extra effort depends logarithmically on the error, and that is a good thing. If it is a power law, it is not a good possibility, because then you have to run the algorithm not a polynomial number of times, but something which will scale as some 1 over epsilon. And if epsilon is written in terms of some digit, 1 over epsilon is depend on the number of digits in exponential fashion, which is not what you want. You want the log 1 over epsilon, which actually means how many digits you want to specify in the final error. So this is just our number system and place value counting. So this is what you can do, and that is a good strategy. So the effort remains polynomial. Now, not only in the number of inputs, but in the number of digits of the output also. This 1 over epsilon after taking log is the number of output digits. And so these are the so-called good algorithms, both in terms of the input and the output number of digits. And this is what you can look for. Can I find an algorithm in this particular class? Now I have a new possibility that I will choose some random numbers somewhere or the other depending on my requirement, and then search for various possibilities. So the random numbers again come in various form. And what I mentioned is just a binary random number which is coin toss. But if you look at various algorithms and libraries, there will be a uniform random number which will give you every time you call some number in the interval 0 to 1. And the distribution is flat, which is what gives a nature that all things are equally likely. This is continuous, this is a discrete, but whenever I say coin toss, it's assumed that the two possibilities are equally likely. And then, of course, there are Gaussian random numbers, which are again specified in some manner, but this will go from minus infinity to infinity depending on the values, but it's concentrated in some particular region. And in the software libraries, there are packages of all those things depending on what you want to use. the important point to remember is they are interconvertible. Okay. So you can have one of them and you can convert into another. For example, if I have a uniform number, I can just make it into binary by saying call the random number and look whether it's bigger than half or smaller than half. Nothing complicated, but I can do it the other way also. If I have a binary random number, I can convert it to a uniform number by saying I will call the binary number 10 times, and the 10 digits will be, or 10 bits will be the values of this binary number, 0, 1, 0, 1, 0, whatever it is. So it will divide this inter uniformly between 0 and 1 in 2 raised to 10 intervals, and they will all be equally likely. So these are the possibilities. And for the software point of view, the discussion is easy. Generating them in hardware is a different question. And there it will depend on the physical mechanism which produces this particular type of random variables, and that depends on various kind of hardware properties. Basically, you will have to take some physical property which you generically call a noise. Noise is basically things which is distributed over various possibilities, and I take that noise and convert it into a device which will produce a random number for me. And how that noise arises and what is its distribution will depend on the hardware characteristics, but that is something which is often done, and it's not a what you call a closed situation. Many people have explored many different possibilities and still they are trying to come up with new possibilities, and well, they have not run out of ideas. It's basically a question of how fast you can produce random numbers. And typically the machines which run at some gigahertz speed, if you want it to give a random number, you have to generate them also at a gigahertz speed, and that is not a trivial task. If you have less requirement of random numbers, you can just use a lookup table or something much simpler, but generating them at a fast rate and having a particular distribution, that is a non-trivial process, and many of the quantum processes are also these days being tried out as a source of these random numbers. The important feature which is needed is something which is more commonly referred to by this acronym IID, which is short form for independent, identically distributed variables. That means when you call this random number first time, the result will be something. When you call it the second time, result will be something else, and those things are not related at all. That's the meaning of independent, and of course you want identical distribution. The first time the same distribution, second time the same distribution, third time the same distribution, etc. If that is not true, you will not call it random. Okay, the correlation between what is going in the first trial and the second trial, then of course it is not something which can be called random. They are correlated. So whatever hardware system that you want to come up with, it must satisfy this property. Otherwise, things can be hidden and the problems, applications can go wrong. And that is a very stringent constraint in developing the hardware for this random number generator. And algorithms are not the only applications. There is a heavy demand for this random number generation in cryptography also. So different subject, but yes, they also need a lot of random number strategies to, hide the message in some peculiar manner, whatever the cryptography does. So this is a definition. Mathematically, this is enough. Physically, certainly not. And that is where the caveats kind of go in, and in some sense the reliability of the algorithm also depends on it. And I can write down some things which you will find routinely, but they illustrate the kind of troubles that are posed by these constraints of random numbers. And I will just give some examples where people have tried out various applications and checked how well they work. And here, the first thing which we use, coin toss. Okay, it's described all over the place. But can you really make the two probabilities exactly equal? Or suppose you toss it and you know all the equations for dynamical motion for the coin, how it is flipping and how it is colliding with the molecules of air. Can you predict what it is going to come out to be? Maybe you can if you know all the Newtonian dynamics in great detail, etc. But you generally don't worry too much about it. Like in a cricket match, now you toss it, it doesn't matter. Maybe it is not 50-50, but as long as you can't predict, it is good enough. So that is the crucial point, that as long as you cannot predict, it can be a good enough choice. If you can predict, everything is gone. So, this is one criterion, and other criterion that it has to be unbiased. If the probability is that it is going to land up on one side more than the other, then it is cheating. Okay? And you may not know it, but these are the things which are very frequently used in gambling, where the user doesn't know but the designer knows the details and they cheat in the sense that is where they make their money. Okay. Otherwise, it is a fair game, then the gambling casino will not earn any money at all. They have to have some margin. Maybe it is not a big margin, but some margin they need. So the question is, can you make this thing unpredictable and unbiased? And suppose it is not, then can you improve it in some particular manner? So they have different answers. So the unpredictability is you need to know the source of and as long as you don't know the dynamics, it's more or less unknown. So what our computer libraries do is actually they use a very simple algorithm to generate random number. You can call that function random number. What does it do? And they basically have started with some initial seed, and they do some addition, multiplication, shifting this way, that way, and give you a final result. The output looks random to you as long as you don't know what was that seed and what was the addition, multiplication they did it in shifting, then it is fine, and those things are buried in the library. They don't reveal it, and then whatever the output you get, well, it looks more or less as you wanted, and that is fine. So these are something called a pseudo that they have actually a deterministic scheme of generating the value for the random number. Only thing is you don't know that scheme, and then everything looks fine, but that is why they are called pseudo-random numbers. Then you can look at some physical process for which you don't know the dynamics, and something which has been used for a very long time. These are called, based on some radioactive process which will occur, but when it occurs, you don't know in advance. Okay, it's just exponential decay rate, and it gives this so-called Poisson distribution for what particle will come out at what instant, and it's a distribution something of this type which you can manipulate to get a whatever random number you want. It's legitimate, and here the unknown part is in this pseudo-random number. There was some equation which produced a number. Here you literally don't know when the radioactive decay is going to occur, and why you don't know, because it's buried in some quantum theory, whatever is going on, and you don't have any knowledge of quantum dynamics beyond a certain point. It's a process which occurs in some sense dictated by certain rules, but also at the same time unpredictable. It may be radioactive decay, it may be something called tunneling also. Tunneling is another thing which is used. Radioactive decay was used in the old days where you literally had a radioactive compound, but then the process was too slow. Tunneling is much more common in the sense that many of the semiconductor devices, they are based on this tunneling diodes, transistors, whatever it is, and they can change states at a much faster rate. And again, it's buried in the quantum dynamics. When it is going to tunnel, you don't know. So that is a part which is unknown. If somebody gives you an equation for when the tunneling is going to occur, well, then all this predictability is lost. So the point is you have to use some process where you don't know the source and all the other things, there's environmental noise. For which you don't know the source because, well, too many things going on. There was no way for you to keep track of what came from where, and just you use one of those variables as your random number. It works most of the time. The other things are like quantum measurement, where you only know the rule that when you measure something, sometime it will go in one eigenstate, sometime it will go in the other eigenstate, and you know the probability. But you can't predict that it will go into this eigenstate, that eigenstate at any particular time. So that is, again, these are dynamical source. It remains unknown, and then it is fine. Okay, so many of the times these genuine random numbers are all connected to quantum effects somewhere or the other, and underlying reason for that is the part of the quantum theory we don't understand. We assign it probabilistic outcomes, and that is what we observe in the experiment, and then it is random. If somebody comes up with a next level of quantum theory which explain how these probabilities are going to occur when you perform a measurement, then all these things will be gone. So that is a story of predictability. Yeah, I can mention one more thing over here in the connection with pseudo-random numbers. There are also examples like given that I can use the digits of some irrational numbers like pi, and the bits are successive bits as some sequence of zeros and ones, whatever it is, and treat them as random, and it works very well, except that if somebody tells me that these numbers are created from pi starting at this particular decimal point, everything is gone. As long as I don't know that the starting point was pi at this decimal point, you perform any test over the whole sequence and it looks perfectly fine. And that therein lies the catch, that the randomness is a crucial label. It cannot be guaranteed because you cannot say that nobody will find out the source of dynamics in some peculiar setting, but it can be certified, and the contrast is between these two words. what does certification mean? It means I try all kind of tricks that I know to find out if there is any correlation, some peculiarity, some bias in the random numbers, and I don't find any of them, then I certify it, that it is okay. And that is the status of any random number generator, whether it is classical, quantum, doesn't matter. All you can do is certify, and these are based on all kind of correlation. So people have done a lot of work trying to figure out good algorithms which can check for some correlations. And whatever the best algorithm you have, if it doesn't find correlation, then you say that this source of random number is certified. Otherwise, you can't say anything more. So, okay, this is one part of the story of what do you need, and this bias. What if your system is not fully symmetric in some particular sense, and the problem in this case is easier. So one can actually come up with very simple algorithm which can eliminate the bias. There will be some amount of wastage, but that we can live with. But that is possible provided you have this criterion satisfied. Independent, identically distributed system where all this other part is already buried in some sense that you have to get rid of all the correlations, and as long as it's independent and identical distributed, then you can get rid of the bias. And I will give you the simplest algorithm for a coin toss, actually pointed out by von Neumann, but maybe somebody else also realized it much earlier. And e.g., I will just look at coin toss. I'll take a situation where 0 in the coin toss has probability p and 1 has probability 1 minus p. P is not half. That is what the problem is. And can I make it symmetric? Okay. So the answer is very simple. So I'll toss the coin twice. If it comes up 0, 1, I will call it the new 0. If it comes up with 1, 0, I will call it new 1, and throw away the other situations where it will come up with 0, 0 or 1, 1. Okay, and as long as these things are independent, the probability of this and this will be exactly equal. And that is fine. I lost something, so 0, 0, and 1, 1 are ignored, and that is a wastage in the sense that I wanted one random number but I used 2. Some overhead, whatever it is, the overhead can be cut down because I can say that this 0, 0 and 1, 1 I will also keep track at the next level where there will be 4 random numbers available, and then I can construct from this pair that one of them is 0, 0, the other one is 1, 1, combine it and the wastage can be reduced. But those are the trivial points. But this is something which is possible, and so people don't worry about bias too much. Main focus is make this as unpredictable as you can, and the rest of the stuff will fall in place. So yeah, this is some amount of mathematical jugglery, but it is important when you are trying to use it in some application that you need this kind of features coming from whatever physical process that produces this random number. Okay. So now let me give examples, okay? Let's suppose this random number is available. Which are the kind of problems in which you get some additional improvement in your efficiency, whatever you want to do. And this is what I kind of mentioned is some branching situations, but I can be more explicit. Again, I'm not going to solve any of the problems, but give some description because certain features are quite generic. So, yeah, let me. This is a very common situation where there is a huge amount of data and you can't afford to analyze each and every component individually because it takes too long. So what people do is sample the data, and from that sample you predict the answer. This is not only, this is related to statistics, other methods which are known as Monte Carlo methods, and generically, this is it's called importance sampling. And then you will get some subset of the whole data, and based on the analysis of the subset, you make statistical statements. You don't have to analyze everything, but you have a reasonably good subset, then you can get a guess for the overall property, and the error will be bounded in some particular manner, so the algorithm then is okay. And they all use this branching process in some particular manner. You have a huge amount of data, how will you pick up some subset? And yes, you will not analyze in a sequential manner, but you pick something over there, then again toss a coin and find some other location and pick something over there and go through the data base and find out some subset, and based on that you calculate some expectation values or averages or whatever based on that. It's a very widespread idea in any statistical analysis, and random numbers are very useful in that, because you don't want the statistics to be biased. The point is you want to make a fair sampling, and then your answers will be useful to a certain extent. And it is not only just a question of mathematics. Many of the physics problems, particularly in statistical mechanics, are studied in this particular manner. Okay, when you say I have some model described by some Hamiltonian or some dynamical equations, etc., how can I predict the answer? Okay. If you have the full space, for example, the model is made of some Ising spins, and each one can take value up or down. So n spins, then there will be 2 raised to n possibilities. You are not going to cover all the 2 raised to n possibilities. You will find a clever subset of that Ising spin configuration, and based on that make a prediction. Okay. So these kind of problems are very common in statistical physics. You study them with this sampling method and random numbers, and those are very useful in the conventional analysis. This is all again classical. We'll see what happens when you try to do quantum stuff on top of that, but this is a big area of the application. The other common area is the problem which are defined on a graph. Okay. And these come from many different sources. The one which I mentioned with the Ising model is something which can be called a local Hamiltonian. So some particular spin is there, it interacts with its neighbors, and some other spin is there, it interacts with its neighbors, and then I can describe it as a graph where the location of each spin is some particular point, and the interaction is the link which connects two neighboring points. And I want to study the kind of features which arise from this kind of interaction. Typically, they are all correlations of certain type because of this interaction. How do I study it? Well, this graph problems actually have connections to this random techniques, and they have this another label which is used in the computer science literature. Is a combinatorial optimization. There are lots of combination possible on the graph, and you want to find some combination which gives you the best result. Okay. So let me give a kind of well-known example called a traveling salesman problem. Defined on a graph, every location is a point, and there are distances between neighboring points. And then I want to find a round trip which has a shortest path. So there are many combinations. There is optimization criteria, find the shortest route. And how will I go through the various possibilities? Well, I will use random numbers. I start here, maybe I will toss a coin and decide to go this way, that way, etc. Count the number of possibilities. I can't afford to go through all possibilities because that is like n factorial, it's too large. But I do some sampling and find not the exact minimum, but something which can be reasonably optimal, then it will have done the job. So there are a lot of problems of this type. So this is a traveling salesman. And they are all defined on this graph with some local structure. So you can sample them in some particular sequence and depending on find some applications. And because of our physical world always has this locality property in the sense that the interactions are there, but they can only be up to a certain distance. After that, interactions become very small. The graph description is very useful in lots of situations. So this is another major class of problems, and there is a third category which actually is possible, which is heavily used. There are a lot of problems which can be formulated as a linear algebra with sparse matrices. It's related to this description also. Why does the sparse nature come in? Because each component only interacts with its neighbors. It doesn't interact with all over the place. But there are many other scenarios which have this particular structure, and well-known example which falls in this category is partial differential equations, where you discretize the derivative as the difference between nearest neighbors, and there is some order of the equation which tells you how many neighbors you need to keep to calculate the partial derivative, but it is local because the number of derivatives in most of the equations which you deal with are bounded. most of the time we deal with only second order differential equations. But as long as we stay in this particular domain, you will have linear algebra with sparse matrices, and there are lots of problems which range from engineering to mathematics, which fall in this particular category, and then they can be tackled using these random numbers. The idea is the same, that this equation may be there, but you don't know the exact answer. Okay, you can't completely solve it analytically. You will put it on a computer, and of course then computer will solve it numerically, but even that if I do it in great detail, it will take too long. So I will approximate in some particular sense. And when we do that approximation, this sampling business will come in. And this stuff is kind of indirectly there in many of the sort of routine algorithms. For example, you ask the computer to do some integral. Okay. Analytically, you can't do it. It will do it numerically. And it will give you some answer. And it will also give you some bound that this answer is correct to so many decimal points. How does it actually do it? So the integral may be defined as a continuous function. The computer is not going to evaluate it all the values. It will evaluate at some subset of values, do some interpolation, some jugglery in between, and then calculate the answer. And then it has chosen an interpolation scheme so that the error is sufficiently small. And then it will give you the guess for the particular accuracy. Of course, it doesn't work if the function is highly irregular, but as long as the function has some smoothness property, it will do the job. So this situation assumes that yes, underlying there is some smooth behavior, and then this sampling of a certain number of points which give you a reasonably good answers. So this forms a very huge class of applications for all sort of randomized algorithms, and well, interesting to study how well you can solve all these problems. First, just using the classical methods, and then can you improve anything by quantum techniques on top of it. Okay. So that is that, and I can give you the inverse example that you can actually use certain class of equations to produce random numbers. Now, mathematically it is fine. How that equation will be realized in a physical system is a different story. Okay. But certain kind of distributions can be produced by specific equations. So the most common example is something which is called a random walk. So this has a associated equation with it, which is called a diffusion equation or a heat equation. What it does is generates some sequence of steps which are called a walk, starting from some particular point, and it can explore a certain region. And that exploration has very useful properties, and which are so You start somewhere, the random walk will explore various possibilities, and what you are interested in is some feature of a transport problem. How far you can go, what is the region you have explored, and you can calculate many other kind of correlations based on the sequence of steps involved in here. And yeah, there is a well-known physical label associated with it called a Brownian motion. And it has a long history. I think Brown observed it by looking at some grain of pollen on water and seeing that it was performing some zigzag motion. And he derived the first case that why it was doing this, because there were collisions between that pollen grain and something in the liquid which was not visible, which are the atoms or molecules or whatever there may be, and those collisions were basically doing scattering. But the scattering was like this random walk. Okay, they were not occurring in a systemic manner. Sometimes collides from this side, sometimes collides from that side, and then they could study how this motion looks like as a function of time. It travels in a certain region, and it has some description. And actually, it was Einstein who made it much more quantitative by observing this Brownian motion and insisting that as a result of these collisions, he could calculate Avogadro's number. From looking at these collisions and how fast it is traveling a certain number, of course not as precisely as you find in the chemistry textbooks these days, but it was a very good mathematical analysis. The answer was not bad. So this has a long history, the random walk, and it has a practical reason from problems in chemistry, because it governs this diffusion, how fast various reagents are going to spread. The heat equation, which is how fast the heat is going to dissipate. All these are practical problems in a lot of science and engineering applications, and studying this random walk is very useful in those particular contexts. So what is this equation? Well, the equation is fairly simple. It's a partial differential equation. And I will write it in, I can write it in multiple dimensions. And there is a proportionality constant which I can add. This is a diffusion constant, okay. Many times this equation is written without a constant over here, because I can redefine my time as d times t, and then the constant will disappear from the equation completely. But this is a equation in terms of mathematical language, it is called the parabolic differential equation. But the simple point to observe is a first order in time and second order in space. And that counting actually immediately gives various features that just the power counting that if you write it a derivative with the second derivative and this is time, I can rescale the time to absorb this value of d, and it will basically tell you that distance is proportional to square root of time. 2 powers here and 1 power there, nothing more complicated than that. And it's an immediate consequence, valid in all these diffusion processes. How far you will travel? Well, it goes as square root of time. Whether you write it as a continuous variable, discrete variable, doesn't make too much difference. This is just a overall scaling behavior. But you can do much more than that. The equation is actually very simple when you use this second derivative operator, which is very common in physics. It's Laplacian. Laplacian occurs all over the place in lots of differential equations, and we can actually solve this equation if you assume that this d is actually just a constant. There are many ways to solve the problem, but the solution which is very frequently quoted is what is known as a Green's function solution, which is let me say phi at x and t equal to 0 is the delta function. That means starting value is a point. And now you are going to wander around. And after that wandering around, you will have some trajectory and you can measure various properties of the trajectory. Even these counting rules like this comes out. But this is a very simple initial condition which allows the exact solution to this equation, and that solution is a Gaussian. And I have to remember that Gaussian function looks like this. The combination of this square of the distance and time, they come together. It's all connected to this particular fact. And so what it does is you start with initial state, which is in this particular case x equal to 0. It will evolve to some distribution like this, and the property of the Gaussian is that width is this is of the order of square root of dt. Again, the same behavior, that is what it is going to result in, and this this is exact. There is nothing mysterious about it, and you can learn many things by studying this result. from, again, a very simple property. So the equation is linear. That means a generic result, I can superpose different components of phi. Nothing goes wrong. As each one is a solution, the sum is also a solution. And this is a powerful framework which is used in a lot of applications. And the only thing which I want to add is this equation is very closely related to the Schrodinger equation. All you do is some constant. I will not. Instead of d, you have another constant. That is fine, but the mathematical derivatives are the same. And this is free particle. The only non-trivial feature is sitting here, square root of -1. And that is enough to label this as a diffusion equation, but that one is a wave equation. As physical phenomena, diffusion and waves are very different. And just putting that thing in changes the dynamical behavior in very non-trivial manner. And that we will look at probably in the next time, what happens in case of a Schrodinger equation compared to this Gaussian business. This power counting is not going to go away. Okay, distance, because that is so what you mean is new name which is given, it is called dispersion, and it just illustrates that if you have a wave packet, something of this thing, the wave packet is going to become broad. That is called dispersion. But the dynamical consequences can be very different, and for that we have to figure out, and this is exactly the solution. What are the solutions of that equation when you solve it with the same kind of conditions, or maybe put it on a discrete lattice as some graph problem? What are the kind of things which will happen? The behavior is very different because well, diffusion is not the same as wave. And we'll see the consequences of that in the next class.
Because of these dispersions in these graph problems, local Hamiltonians,
Yeah.
we get these many combinations. Because of
All those things will remain. The quantum case, they are not going to go away, but the dynamics, the interpretation will come out to be very different. You can still have a local Hamiltonian, you can still have a graph problem, you have the interaction, but what is the meaning of the evolution? You have to understand it all over again.
are we getting many combination of evolution in local Hamiltonian problem?
Yeah, the evolution changes, yes. And that is because this is a dissipative process. The diffusion equation or something like that, or a heat equation, etc. But the solution of that is going to be a unitary process. And there's a big difference between a dissipative dynamics and a unitary dynamics.